Hey guys, before we continue to the next topic, I just wanted to touch on that box that I sort of skimmed over last time. Actually, it was in the right place. I just had kind of confused myself with my own notes. But I just want to point out something real fast. So, in the definition for logarithm up above, we had f(x) equals to log base a of x, where a is bigger than 0, a can't be 1, right? I just wanted to point out that remember the definition for exponential functions, where f(x) equals to a to the x? We also had the same stipulations, right? A is bigger than 0 and a cannot be 1. And then look at the domains. The domain for exponential function, remember, was negative infinity to positive infinity, and the range was 0 to infinity. Well, look at the domain and range for the logarithmic function. Domain is 0 to infinity, and range is negative infinity to positive infinity. And this all makes sense because if you think about it, remember we've mentioned that these guys are inverses of each other. Well, inverse functions, they have opposite domains and ranges, right? So it all kind of comes together. The other thing I want you to note here is, check this out. When a is bigger than 1, that base, then the logarithmic function is strictly increasing on its domain, right? Well, same thing happened before, right? For exponential functions, when a, the base, was bigger than 1, then it's strictly increasing on its domain, which in that case was everything, negative infinity to positive infinity. And when a is between 0 and 1, so positive fraction basically, right? Positive fraction less than 1. And same thing for here, positive fraction less than 1. Then both of these functions are strictly decreasing. So that applies for both of them. So just kind of want to point that out to you. Okay, let's move on to the next topic. Next topic is to find the domain. And actually, I'm sorry, guys. I actually changed this. I'm only going to do domain. And generally, the range is not too difficult to find. If it's just a single function, it's usually just going to be negative infinity to positive infinity. But there are some things that do kind of make it a little more tricky. So we're just going to skip over that part and focus in on finding the domain. Now, how do you find the domain? Let's again recall just the basic function. So if we look at the basic function of log base a of x, remember that domain is 0 to infinity, right? And what that's saying is that 0 to infinity just means that you're bigger than 0, basically, right? That's just two ways of saying the same thing. This x here inside is the thing that's bigger than 0. So I take log base a of some value inside. That value inside has to be bigger than 0. Now, what if that value inside isn't just a regular old x? What if it's something more complicated? And here I have just a placeholder. I just chose this smiley face. So what if you have log base a of something else that's not just x? Well, that thing that's in there, that should be bigger than 0, right? So how do you find the new domain? Well, whatever that thing is, you just solve that inequality. So let me give you a simple example. What if it's x minus 1 in there? Right? What if that smiley face is x minus 1? Well, you're solving the inequality x minus 1 is bigger than 0. That means x must be bigger than 1. Now, what does that mean though? What does minus 1 mean? If I have log base a of x minus 1, just think about your rules of transformations. This minus 1 means everything got shifted to the right by 1. So whereas your original log function would look something like this, passes right through 1, 0, right? It goes like this. It's got a vertical asymptote right at 0. Well, if I have a minus 1, that's going to shift this whole thing over by 1. So it's going 1 to the right. And now I have a new vertical asymptote right here at positive 1. And my domain now is then 1 to infinity. Or in other words, x is bigger than 1, right? So how did I get there? I just got there by solving that inequality. Starting whatever is inside, make sure that's bigger than 0. And that just corresponds exactly with the kind of transformation that occurred. So let's try the questions 9 through 13 with that in mind. Where were we? Down here, okay. It says find the domain of the given functions. Okay, nice and big here. Starting with number 9. And number 9 very similar to what the example I just gave you, right? The base here is not really that important. It's always going to be something that's positive and not equal to 1. Okay, so whatever the domain is, whatever this base is, I just want to make sure that this inside portion is bigger than 1. So I'm going to solve the inequality x minus 8. I'm sorry, did I say 1? I meant 0, sorry. X minus 8 is bigger than 0. Okay, so solve that thing. Add 8 on both sides. I got x is bigger than 8. Now as an interval, that's from 8. Okay, rating 0, sorry. That's from 8 onwards to infinity, right? And the 8 and infinity look very similar, except one is sideways. Okay, so 8 to infinity, that is your interval. That did not look great. Let me try that in a box instead. Okay. And not including 8 because you're never going to actually touch 8. Okay, let's move on to number 10. Okay, number 10. Okay, number 10. Number 10, notice that you have 2 separate logs, right? You got 2 separate logs. So what happens if you're adding 2 together? Well, what you're going to do is just take the more restrictive of the 2. Right? Or, another way to say that is to say you're going to take the overlap of their domains. Because the whatever the domain is, right? It's got to satisfy this portion, this whole function. It's got to be in the domain for that part, and it's got to be in the domain for that part when you add 2 different functions together. So we're going to do this. We're going to say x minus 2 has got to be bigger than 0. And at the same time, 2x minus 1 should also be bigger than 0. That's just another way of saying the same thing I was already telling you guys, yeah? So let's do that one at a time. X minus 2 bigger than 0 means x is bigger than 2. Okay, easy. 2x minus 1 bigger than 0 means 2x is bigger than positive 1, right? Moving 1 to both sides. Divide by 2, x is bigger than a half. Okay, so where do those guys overlap? Let's just sketch this on a number line real quick. And I can tell you right now, the answer is from 2 onwards, but let's just sketch it. Okay, here's a half, right? If you want, yeah, let's just write our 2 numbers. Here's a half. Somewhere to the right of that is 2. The first guy here, x bigger than a half, that says, okay, not half, but you got to be bigger than that. So that area right there. The second portion, bigger than 2 means, okay, not 2 itself, but bigger than that. So that portion. And now, in order to satisfy both, you got to have both colors. You got to have red and black, right? And that only means this portion here. So to the right of the 2. You can't be over here in this area because it's not satisfying this black region and you're not bigger than 2, right? You can't be over here because then you're not satisfying either. You got to be only on the right-hand side. So what is your overall domain then? Domain is you got to be bigger than 2. So 2 to infinity. Okay, moving on. Number 11. Oops, missing parentheses here. Okay, number 11. Kind of similar situation here. We've got the domain for this, domain for that. For the first part, it's number 11. X plus 1, that guy's got to be bigger than 0, right? And second part, the square root of x plus 5 has got to be bigger than 0. Okay. Now, note here. I kind of want to just make a small note here. I have a square root here, yeah? So because of the square root, we know inside square root it's also got to be positive, right? So this part here it's also got to be positive. But, it's actually not going to matter. Maybe let me make a note of that. Note that x plus 5 should be bigger than 0 because that's inside of a square root, right? Bigger than or equal to 0. So that's whatever my final result is, it should also satisfy that. But, it's not going to matter in a second because how would you solve that thing? Well, you square both sides to get rid of the square root, right? But 0 squared is still 0. And x plus 5, the square root of that squared is just x plus 5. So then, in the end, x plus 5 bigger than 0, that already accomplishes this necessity that x plus 5 is bigger than or equal to 0. All right, let's finish solving those two things. Since I'm already working the right side, let's wrap that thing up. Minus 5 from both sides, x is bigger than negative 5. Here, x plus 1 bigger than 0 means x is bigger than negative 1. Okay, so same thing. I'm going to visualize this as a number line here. Which one's to the left, which one's to the right? Here I've got negative 5 over here and negative 1's over here, right? So I'm going to be bigger than negative 1. That's this part here, onwards to the right. And I got to be bigger than negative 5. That's this part onwards. But I've got to accomplish both those things. This area is out. The only part that counts is from the negative 1 onwards, because that's the part that has both shadings. So what is my overall domain then? The domain is negative 1 to infinity. Now, do I include negative 1? The answer is no, because you got to be strictly bigger than negative 1. Right, you're not allowed to be... In the original logarithmic functions, you can't be 0, right? And that's essentially what this is, just shifted to the right. You can't be, or did I say right? I meant left. Yeah. Okay, 12. Oh, interesting question. So I got the log of the absolute value of x. But same approach, right? This inside of the log function has got to be bigger than 0. Now, when is the absolute value function bigger than 0? Well, pretty much always, except when it is exactly 0. So x cannot be 0 itself. Because if it's 0, then it's not greater than 0. It's exactly 0. But if x is negative, well, absolute value is going to force it to be positive. So no issues there. Now, if you want to be more rigorous about this, the way that we typically solve absolute value questions is, you might have forgotten this. We just we split into two. We say, okay, x is bigger than 0, the original, right? And we say negative x, and we switch to inequality and then say negative. But in this case, it's 0. So I've got negative x is less than 0. If I multiply both sides by negative 1, which is actually, sorry, what I did. No, I did do that. It's just negative 0 is 0. Multiply both sides by negative 1, I get x is less than 0, right? And this original thing was still just x is greater than 0. It's already solved. So looking at those two solutions, what does it mean? X is less than 0 or x is greater than 0? It means it's not equal to 0. Yeah. Okay, how do you write this in interval notation? You can say negative infinity to 0, union 0 to infinity. But in this particular case, just saying x not equal to 0, that's good enough for me too. That means the same thing. Okay, last one for this topic and this video. This is question 13. ln of x minus 2 over x. What's the domain for that? So same approach again. I'm going to take this inside part, make sure that's bigger than 0. In this case, how do you solve this though? Well, this is a case where it helps to kind of remember the graph, and because I'm comparing to 0, I just want to think about positive and negative. Now, warning here, guys, it's very tempting to think, oh, okay, why don't I just multiply both sides by x, right? And then, because then that would just make this part disappear. And I get x minus 2 bigger than 0, right? Because 0 times x is just 0. So I'm like, I think that's going to work. But no, actually, no, that's not going to work. That's not going to work. Because you're losing information there when you multiply by x, because multiplying by 0 disappears at x. You actually don't... that means it wouldn't matter what that denominator was, right? But in reality, you do want to keep the information. What does this mean? This is a graph of it kind of looks similar to it's a rational function graph, right? Which we've seen before, where either the top and bottom, same power, it's got an oblique asymptote. It's something that we need to be a little more careful about. Now, what is the proper approach? Proper approach is just to think about when is the top 0, when is the bottom 0 asymptote, and then think about test points to the left and right of those. Okay, so first of all, when is the top 0? Top is 0 when x is equal to 2. So 2 is a spot, important place to check. When is the bottom 0? When x is equal to 0. And in between, I got to make my checks. So obvious choice would be 1 right in between there, and then 3 to the right of the 2, and then a negative 1. Okay, so one by one, what happens? If I'm negative 1 over here, negative 1 minus 2 is negative. On the over x is negative. That's overall going to be positive over here. Okay, what if I put in 1? 1 minus 2 is negative. Over 1, that's positive. So that's overall negative. Negative over positive. If it's 3, 3 minus 2 is positive. Over 3, that's positive. So overall positive. So where were you positive? To the left of 0, right? To the left of 0. And to the right of 2. But what about 0 and 2 themselves? Well, if you're exactly 0, you're undefined. And if you're 2, you're exactly 0. And neither of those things is what we want, because we want to be bigger than 0. So that means overall the domain is negative infinity to 0, open parentheses, union with positive 2 to infinity. And there you go. Okay, that's it. See you in the next video.